A very good day, everyone. Myself, Darshini R, and this presentation covers our construction project execution, monitoring, and control studio project based on a bridge construction project. The project focuses on analyzing execution strategies involved in bridge construction, particularly in the areas of equipment planning, contract administration, sustainability integration, and labor compliance. The objective of the study was not only to understand the engineering aspects of bridge construction, but also to evaluate how planning decisions, contractual conditions, and sustainability measures affect project cost, time, and execution efficiency. Involves the construction of a 300-meter long bridge connecting Village A and Village B across a river. The bridge consists of an 80-meter main span and 220 meters of approach roads. The total width of the bridge is 12 meters, including a 9.5-meter carriageway and a pedestrian footpath. The project is a brownfield infrastructure project executed under an item rate contract with a budgeted cost of approximately 22.72 crore rupees. One of the major objectives of the bridge is to ensure uninterrupted connectivity between the two villages throughout the year, especially during monsoon conditions when the river overflow causes isolation. The bridge includes retaining walls, pile foundations, open foundations, piers, and expansion joints at regular intervals. The total project duration considered for execution was 18 months. On to the equipment planning. Before selecting equipment, the major site constraints were identified. The project site had restricted working space near excavation zones, riverbed conditions, linear bridge alignment, and multiple simultaneous working fronts. These constraints directly affected equipment movement and productivity. Therefore, equipment selection was done based on mobility, lifting capacity, operational efficiency, and suitability for confined bridge construction conditions. The slide also shows the operational cycle time and daily operating cost of major equipment such as hydra crane, backhoe loader, and concrete mixer. Additionally, idle costs were analyzed because bridge projects often experience delays due to weather, sequencing dependency, and inspection approvals. This helped in deciding whether equipment should be owned or hired. For the excavation activities, equipment selection was carried out based on required productivity and total excavation quantity. The proposed equipment included one hydraulic excavator, three tipper trucks, one backhoe loader, and one vibratory roller. A comparison between owning cost and renting cost were performed for each equipment. Based on utilization duration and operational demand, owning was found to be more economical for continuously used equipment such as excavators and tipper trucks. The total excavation quantity was approximately 4,040 cubic meters. Considering equipment productivity, field factors, and finishing allowance, the excavation duration was estimated as 6 working days. The equipment selection process ensured reduced idle time, continuous workflow, and efficient earthwork execution. Operations, the peak concrete demand was analyzed monthwise to determine equipment capacity requirements. The selected equipment included a 30 cubic meter per hour batching plant, transit mixers, boom placer, concrete pump, and vibrators. The selection was based on the project's peak daily concrete demand of approximately 109 cubic meters per day. A cost comparison was also performed between ready-mix concrete procurement and on-site batching plant operation. Using an on-site batching plant reduced the concrete cost by approximately 600 rupees per cubic meter. This resulted in gross monthly savings of approximately 4 lakh rupees and net savings of approximately 1 lakh rupees per month. Therefore, owning a batching plant was considered economically beneficial due to continuous concrete demand during bridge construction. This slide explains the reinforcement processing and steel yard planning. The reinforcement workflow included unloading, stacking, cutting, bending, threading, cage fabrication, and shifting to work locations. Equipment such as bar cutters, bar benders, threading machines, welding machines, and hydra cranes were selected based on daily reinforcement demand. The project required approximately 333 metric tons of steel with a peak demand of 2 metric tons per day. The selected equipment provided a processing capacity of around 14 to 15 metric tons per day, maintaining a buffer capacity for uninterrupted execution. The decision to hire certain equipment instead of owning was based on intermittent utilization and short operational duration. Section focuses on contract administration and risk analysis. The project was studied under an item rate contract structure. The contract administration process included pre-bid analysis, scope definition, bid submission, execution monitoring, payment management, change management, and dispute resolution. The RAble approval workflow involved multiple approval levels including PMC, additional engineer, deputy city engineer, and billing department approvals. Several special contract conditions created financial risk for the contractor. These included no idle charge clause, retention money, security deposits, long defect liability period, and absence of machinery advance. Such clauses increases contractor cash flow pressure, procurement burden, and financial exposure during execution. This slide also explains the claim management and arbitration procedure followed in case of disputes. This slide explains price adjustment and additional item analysis. Extra items such as electrical poles and LED lighting systems were identified during execution. The total additional cost for these items was approximately 12 lakh rupees. Price adjustment formulas for material such as steel, cement, and bitumen were also studied. For example, due to market fluctuation, the actual steel cost exceeded the base contract rate. However, the price adjustment clause partially compensated the contractor for material escalation. Focuses on sustainability measures incorporated into the project. Water conservation measures were studied with respect to the targets from SDGs. The proposals are as follows. Using curing compounds instead of conventional curing resulted in water savings of approximately 5.7 lakh liters and cost savings of around 74,000 rupees. Additionally, sedimentation tanks and RO systems were proposed to reduce water wastage and improve resource efficiency. Energy sustainability was analyzed through solar panels and green power tariff. The solar panel system reduced annual carbon emissions significantly while also providing long-term economical benefits, being it the sustainable alternative to the conventional grid power usage. Focuses on sustainability measures under material and labor compliances. The strategies were analyzed under reduce, reuse, and recycle principle. To reduce material consumption and carbon emission, fly ash blended cement, BIM optimization, precast elements, and just-in-time procurement were considered. Reuse strategies included reusable steel formwork, recycled slurry, and reuse of excavated soil. Recycle strategies included recycled concrete aggregate, RAP in roadworks, and steel scrap recovery. This slide also explains labor management and statutory compliances during execution. The labor compliance process was divided into pre-construction, mobilization, execution, wage payment, monitoring, and inspection stages. Documentation such as labor license, insurance records, attendance registers, wage registers, and overtime records were maintained throughout the project. Regular inspection and compliance verification ensured legal compliance and minimized labor-related disputes. This process also improved workforce transparency and material monitoring efficiency. Conclude, this project demonstrated how effective execution planning plays a critical role in infrastructure construction projects. Through detailed analysis of equipment planning, contract administration, sustainability strategies, and labor compliance, the project evaluated how technical and managerial decisions influence cost, time, productivity, and environmental performance. The study highlighted that successful bridge execution depends not only on structural design but also on efficient resource planning, risk management, and sustainable construction practices. Thank you.